Alright, so this is our second video on internal resistance. In our last video, we looked at what is EMF and how our internal resistance affects the EMF. We looked at what happens to our EMF and our terminal voltage when our external resistance becomes larger and larger and larger, and also how that affects the current throughout the circuit, okay? And that was depicted by this graph right here, okay? And so in the last video, we looked at current and voltage. However, in this video, we're going to look at how internal resistance affects the power of components, okay? So the amount of power that they draw. So let's imagine we have a 10 volt cell, okay? This has a resistor over here. This is 10 volts. And let's say this is 200 ohms, okay? And let's say we have an internal resistance of 1.4 ohms, like so. And because this is internal resistance, we're going to put a little box around this, okay? So remembering from our last video that our internal resistance can be modeled as a resistor, remembering that our internal resistance is the resistance of the cell plus the resistance of the wires, okay? Because we know that in real life that our power supplies and our wires aren't ideal, meaning that they actually have resistance in real life. And so we can model that resistance as our internal resistance, okay? And so therefore, from here, we can say that our EMF is equal to 10 volts, okay? And as discussed in the previous video, this is only 10 volts when our current is equal to 0 amps, okay? And so from here, we can calculate our current pretty easily. Remember that V is equal to IR, and therefore our I is equal to V all over R. Remember, this is our total resistance, okay? And our total resistance is going to be the resistance of our external resistor plus our internal resistance. And so that's 200 plus 1.4, and that gives 201.4 ohms. Okay? And so therefore our current is equal to 10 volts all over 201.4. Okay? And this gives a current of 0.049 amps. Okay? And so now from here, we can calculate the voltage across our internal resistance. And what this will do is tell us how much volts are being lost due to the internal resistance, and therefore we can calculate our lost volts, okay? And then once we calculate our lost volts, as we can see here, our terminal voltage is equal to the EMF minus our lost volts. And so we can calculate our EMF that way. And so therefore, to calculate the voltage drop across this internal resistor, we obviously would use V is equal to IR. As this is a series circuit, because charge can only flow in one direction, our I is going to be this I value that we just found. And so that's going to be equal to 0.049 multiplied by the resistance, which is 1.4. And this gives a voltage drop of 0.07 volts. And so therefore, our terminal voltage, which is TV, okay, for short, is equal to 10 minus 0.07, and that's equal to 9.93 volts. There we go. Now also in the last video, we saw that the terminal voltage was equal to the voltage across our external resistor, okay? And so therefore, this is our terminal voltage also, okay? And so therefore, V is equal to IR. Again, our current going through this resistor is the same as the current going through our internal resistance. And so the current value is the same, 0.049, times 200 ohms. And this gives a voltage of 9.93 volts once again, okay? So we have two ways to calculate our terminal voltage. So now moving on to a more complicated example and now calculating the power of components, okay, like I said in the intro, we're going to move on to a scenario where it's a simplified diagram of what happens in a car, okay? So we're going to have a car battery over here with some sort of internal resistance, okay? And that's going to be hooked up to a switch, which this switch can sort of be like our key to our car, okay? And then we're going to have a motor, which is going to be our starter motor, okay? The motor that helps the engine start to turn, okay? And then we're going to put a lamp here, which can illustrate our headlamps for our car, okay? Like so. And let's say this lamp has 0.9 ohms of resistance. This internal resistance, okay, let's draw the box around. This internal resistance, R, little r, has 0.1 ohms of resistance, and this is a 12 volt supply, and this motor has 0.1 ohms of resistance also. Okay, so there is this phenomenon that happens that when your car lights are on, but the engine is off, okay? So your car lights are on, but the engine is off, and then you turn on your car, your headlamps will actually go dim before going back to bright again, okay? And so the question that we want to answer is, why does headlights, okay, which is our headlight right here, okay, go dim when car is starting, okay? And so when the car is starting, that is when our starter motor is engaged and the switch is closed, okay? So when starter motor engaged, okay? So first things, we can look at what happens before the starter motor is engaged, okay? And so that is when the switch is open, okay? So before starter motor engaged, and that is when the switch is open. Okay, and so first thing we should know from our previous years that the brightness of a lamp is due to the power in the lamp, okay? And we obviously know that power is equal to IV, okay? And obviously Ohm's law is V equals IR. And so if we substitute this V into this equation, we get P is equal to I multiplied by IR, and therefore P is equal to I squared R. Also, we can rearrange for I, and we get I is equal to V all over R, and therefore substituting this into here, we get P is equal to V all over R multiplied by V, and we get P is equal to V squared all over R, okay? And so from here, we get our 3 power equations, okay? So now going back to before the starter motor is engaged, okay, and that's when the switch is open like we see here, we can calculate our total resistance in the circuit, and as we can see here, this branch is open, and so therefore the resistance of the motor is not considered in the equation, and so we simply have the resistance of the bulb and the internal resistance, and so we have 0.9 plus 0.1, and that's equal to 1 ohm of resistance, okay? And therefore we can calculate the current, and that's equal to V all over our total resistance, and our voltage is 12 all over our total resistance of 1 ohm, and this equals to 12 amps of current. And as you can see, when this switch is open, we have a series circuit, as there's only one pathway for a charge to flow, and so therefore the power of this bulb we can find using P is equal to I squared R, okay? We found the current through this bulb. As this is a series circuit, we have 12 ohms coming in, okay? And we obviously have the resistance, and so that's equal to 12 squared times 0.9, and that's equal to 144 times 0.9, and that's equal to 129.6 watts. There we go. Okay, so now we found the power before the starter motor is engaged. So now when starter motor engaged, okay, and this is when the switch is closed, okay, so now the switch is in the closed position, like so. We can calculate our total resistance, okay? Now, as we can see, the motor and the bulb are in parallel, okay? Be careful, this internal resistance is not in parallel with the motor and the bulb, okay? The reason for that is because our bulb and our motor share nodes on both ends, okay? They share this node right here, okay? And again, if you want more on this, you can look at my video on what is a parallel circuit, okay? As we can see here, our internal resistance does not share both of the nodes. It shares this node right here, okay? However, it does not share this node, okay? Because we can see here that our power supply is in the way. And so therefore, as our starter motor and our bulb are in series, we're gonna calculate them like that, plus our 0.1 ohms for our internal resistance, okay? And this gives a total resistance of 0.19 ohms, okay? So now, what we can do is calculate the current going into our power supply, okay? So the current entering our power supply. And obviously the current entering our power supply is equal to the current leaving our power supply, okay? And so we can calculate that current right here, and that's equal to V all over R. It's going to be equal to the voltage of the circuit, which is 12, divided by the total resistance, which is 0.19, and that's equal to 63.16 amps, okay? And so now that we have the current going into the power supply, we can now calculate the voltage drop due to our internal resistance. And that is exactly what we did in this scenario right here to calculate our terminal voltage, okay? And so therefore, our V is equal to IR, and our current is what we just found, 63.16, times our resistance of 0.1 ohms, because that is the internal resistance right here. And this gives a value of 6.32 amps, okay? And so therefore, our terminal voltage is equal to 12 minus 6.32, and this gives a terminal voltage of 5.68 volts, okay? And so therefore, this is our terminal voltage, like so, like this. And so therefore, due to the definition of what makes components in parallel, this is the same voltage that is across our bulb, okay? If you need to, you can pause the video to think about why that is. Alright, as we can see here, these 2 points share a node because they're connected via an ideal wire, and therefore these 2 points also share a node because they're connected via an ideal wire. Okay, and again, if you want more information on what makes components in parallel and what is a node, you can watch my video on what makes a parallel circuit. Okay, and so therefore, as we now know the terminal voltage, we can use this equation right here to calculate the power of the bulb. Okay, and we get P is equal to V squared all over R, and this gives 5.68 squared all over 0.9, and this gives a voltage of 35.9 watts. All right, there we go. And so as you can see from our 2 values right here, okay, let me draw that bigger. We have a before, that was 129.6 watts, and our after was 35.9 watts. As we can see, when we had our headlamps on, before the starter motor was engaged, our headlamps were producing almost 130 watts, and so therefore that would be a given brightness. And then once the starter motor is engaged, our headlamps drop to 35 watts, okay? And so that would be seen as a reduction in brightness, okay? And then afterwards, once the car is running, the starter motor will be disengaged, and therefore it should go back to 129.6 watts, okay, when you're driving. All right, so that would be it for this video. In this video, we saw how the internal resistance can have a major effect on how much power each component draws in a given circuit. Okay, see you.